Hello everyone, welcome to MBAN 109, and for today's video, we'll review about the dot product and cross product. So first, we have A, B, and C be vectors in R3, and let's suppose small c be a real number scalar. The dot product or scalar product of two vectors A and B yields a scalar quantity and is given by A1B1 plus A2B2 plus A3B3. The dot product has these following interesting properties. First is that it is commutative. Next is that it is distributive over addition or subtraction. Third one is that it is associative with scalar multiplication. Fourth is when a vector, let's say vector A, is dotted with a zero vector, we get a scalar zero. Note that the dot product always yield a scalar quantity. Lastly is if we have a vector dotted with itself, then we obtain the square of its norm or its magnitude. We can find the angle between two non-zero vectors, theta, with the use of the dot product. So it is given by this formula right here. We have cosine theta is equal to the dot product of A and B divided by the product of the norms of vectors A and B. Here, theta is inclusive. It is between 0 and pi. Vectors A and B, given that these two vectors are non-zero, they are parallel if and only if theta is equal to 0 or when theta is equal to pi. So if theta is equal to pi, then A and B are opposite to one another or they are anti-parallel. Next is when vectors A and B are perpendicular or orthogonal to one another if and only if theta is equal to pi over 2 or dot product A and B is equal to 0. Next, we have the vector projection of B onto A. So it is given by this formula right here. Its definition is that the vector projection of B onto A is the perpendicular projection of the position representation of vector B onto the line containing the position representation of vector A. So what does that mean? So let's say we have a vector, let's say we have vector A right here and the line which contains it. So the vector projection of B onto A is just the shadow that vector B casts on the line where the vector A sits onto. So this one right here is the vector projection of B onto A. So if we know the angle between vectors A and B, let's say right here we have theta is acute, or when theta is between 0 and pi over 2, the vector projection of B onto A has the same direction with vector A. Next is when theta is equal to pi over 2, or vectors A and B are perpendicular to one another. Given that vectors A and B are non-zero, the vector projection of B onto A is the zero vector. Note that the vector projection of B onto A is a vector quantity. Lastly is when the angle theta between vectors A and B is obtuse, or when theta is between pi over 2 and pi, the vector projection of B onto A points opposite that of vector A. So next, we have the scalar projection of B onto A. It is just the norm of the vector projection of B onto A. So it is given by this formula right here. We still have the dot product on the numerator, but this time the denominator only contains the norm of vector A. So moreover, any vector can be decomposed into its orthogonal components with respect to another vector. So here, for example, we can express vector B as the vector projection of B onto A and the difference of vector B with its vector projection of B onto A right here. So you can see they are orthogonal to one another. So we can express vector B as the sum of these two. Okay, that would be it for the dot product. Next, we go to the cross product. So the cross product of A and B is a vector, which is given by the determinant of this matrix right here. We can use the diagonal method. We can extend the components of A and B here. For I, we have A2, B3, and if we go opposite to that direction, it is negative. We have A2, B3 minus A3, B2. For J, we have A3, B1 minus A1, B3 right here. Lastly is for the K or the Z component, we have A1, B2 minus A2, B1. So this vector right here, A cross B, is orthogonal to both vectors A and vector B. So the cross product also have its own set of properties. Number one is that it is anti-commutative. So it is not like the dot product, which is commutative. So the order really do matter for the cross product. However, for the properties 2 and 3, it's just the same. The cross product is also distributive and it is also associative with scalar multiplication. For the properties 4 and 5, we have these interesting ones. So if we cross a vector with a zero vector, or if we cross a vector with itself, both of these will yield the zero vector. So note, it will yield a zero vector, not a scalar zero. Okay. So for the applications, we have this. So the norm of the cross product A and B is just equal to the product of the norms of A and B and the sine theta, where theta is again the angle between two non-zero vectors A and B, and it is inclusive between 0 and pi. So the two vectors are parallel if and only if the cross product is equal to the zero vector. So why is it so? You know that two vectors are parallel if theta is equal to 0 and sine 0 is just equal to 0. So if this one right here in the right hand side of the equation is equal to 0, that means the magnitude of the vector is equal to 0. So what vector has a magnitude of 0? Yep, that's right. It is the 0 vector. So trivially, the 0 vector is considered to be parallel and perpendicular to all non-zero vectors. The second application of the cross product is that we can find the area A of the parallelogram having sides vectors A and B, which is given by the norm of the cross product. We can extend this idea so that we can find the volume V of a parallelepiped with adjacents A, B, and C. So it's given by the scalar triple product right here. So here, B and C is the base of the parallelogram, and A, vector A here, is the height of the parallelepiped. Okay? So it is given by the determinant of this matrix right here, or this one right here. So as you can notice, this B2C, B3, this difference right here is the cross product. And we apply the dot product here of A. So we have A1 multiplied to this one, A2 multiplied to this one, and A3 multiplied to this one right here. And then we add them all together since it is dot product. Lastly is we apply the absolute value to get the volume. So later on, we were going to solve the volume of parallelepiped, so we can apply this concept right here. Meanwhile, let's solve problems now. So for the problem number 1 from physics. So work is given by W is equal to F dot B. Suppose a force F is equal to 4I hat minus 6J hat plus K hat is applied to a crate that moves from the origin to point Q, which is equal to the coordinate 2, 1, negative 5. We are tasked to find the work done on the crate and also to find the angle between the two vectors F and D. So if you have time, you can pause this video and solve for yourself. But for now, we are given the dot product, the formula of the work, which is the dot product of F and D. We already have the vector F, so we are to find the vector D. So the vector D is equal to the vector PQ, where P is just the origin and Q is given. So for easier shortcut right here, we will just copy the coordinate of Q and put it in a position representation. We could also write vector F as in that way. So we can now find the work. So work is just that product of vectors F and D. So we apply the formula. We have 4 times 2 is equal to 8. Negative 6 times 1 is equal to negative 6. 1 times negative 5 is equal to negative 5. We add them together. We have 8 minus 6 is equal to 2. 2 minus 5 is equal to negative 3. So we obtain a negative work. So this implies that the angle between the vectors, the force and the displacement, is obtuse. So we can verify it on the next subproblem, which is to find the angle between these two non-zero vectors. So it is given by this formula right here. And since we already have the dot product of F and D, we are left to find the norms of the vectors F and D. So it is just the square root of the sum of the squares of the components right here. So for the vector F, it has the magnitude of square root of 4 squared plus negative 6 squared plus 1 squared. So we evaluate that. We have square root of 53. We do the same for the vector D, which is equal to 2 squared plus 1 squared plus negative 5 squared. We have square root of 30. So these two radicals cannot be simplified further. So we compute for the angle. We plug those values to the formula. So we have negative 3 all over the square root of 53 multiplied by the square root of 30. We multiply this together in a one big radical. So we have negative 3 all over the square root of 1590. and we rationalize the denominator, or we multiply both numerator and denominator by the square root of 1590. We get this one, so square root of 1590 multiplied by itself, we cancel the radical. And since 1590 is divisible by 3, we can simplify it further. We get cosine theta is equal to negative square root of 1590 all over 530. So this is just the cosine of theta, but we are asked to find theta, which is inclusive of 0 to pi. Since negative square root of 1590 all over 530 is in between negative 1 and 1, the value of arc cosine of this value exists. Moreover, the arc cosine of x, its range is in between 0 to pi for all x which is in between negative 1 and 1. Therefore, theta is equal to the arc cosine of the negative square root of 1590 all over 530. So if you use a calculator, you can approximately find theta, which is approximately 94.3 degrees. So indeed, theta is obtuse because cosine theta is negative. That is, theta is greater than pi over 2, which is in line with our answer in the first sub-problem. Next, we have problem number 2. We let A be a vector 4, negative 1, 5, and vector B equal to 2, 3, negative 3. We express B as a sum of two orthogonal vectors, one of which is the vector projection of B onto A. So the vector projection of B onto A is given by this formula right here. So we solve first for the dot product and then the norm of the vector A. So we solve for the dot product right here. We have 4, negative 1, 5 dot with the vector 2, 3, negative 3 of 4 times 2 is equal to 8. Negative 1 times 3 is equal to negative 3. 5 times negative 3 is equal to negative 15. We add them all together. We have 8 minus 3 is equal to 5 minus 15 is equal to negative 10. And then we find the norm of the vector A. This is just the square root of 4 squared plus negative 1 squared plus 5 squared. We evaluate it into square root of 42. Now we have these values. We plug these back to the original formula of vector projection right here, like that. And since we are to square the denominator, the radical sign will just cancel. And then we can simplify this fraction, negative 10 over 42, into negative 5 over 21 and apply scalar multiplication. We distribute the scalar into the vector, and then we get negative 20 over 21, 5 over 21, and negative 25 over 21 as the components for the vector projection of B onto A. Since we are tasked to decompose vector B as a sum of two orthogonal vectors, and we already have the vector projection of B onto A, we then find the difference of vector B with a vector projection right here. So we distribute it, we apply vector subtraction here. 2 minus negative 20 over 21, 2 is just 42 over 21, and double negatives is positive. We have 42 plus 20 is equal to 62. 3 minus 5 over 21, 3 is just 63, so 63 minus 5 is equal to 58. And then negative 3 is just negative 63, and negative minus the negative is just positive. So negative 63 plus 25 is equal to negative 38. So these fractions right here cannot be further simplified. So we can express vector B as this sum right here with these values right here. So you can verify this. So if you add this together, you will get the components of vector B. Lastly is we are tasked to find the area of the parallelogram whose adjacent sides x is equal to 2, 1, 4 and y is equal to 5, 1, negative 2. And for the next sub-problem, we are tasked to construct a parallelepiped with height of z is equal to 1, 1, 3, and we are tasked to find its volume. So to find for the area of the parallelogram, it is given by the norm of the cross product of x and y. So first, we find the determinant of this matrix. We apply the diagonal method right here. So we extend these two components right here. So we have 1 times negative 2 minus 4 times 1. Next, we have 4 times 5 minus 2 times negative 2. Next is we have 2 times 1 minus 1 times 5. So we have 1 times negative 2 is just negative 2. 4 times 1 is 4. So negative 2 minus 4 is equal to negative 6. 4 times 5 is equal to 20 right here. 2 times negative 2 is negative 4. 20 minus negative 4 is just 24. And then 2 times 1 is 2, and 1 times 5 is 5. 2 minus 5 is just negative 3. So the cross product of x and y is a vector with components negative 6, 24, and negative 3. Since we are tasked to find the area, we find the norm of this vector. We have square root of negative 6 squared, which is equal to 36. 24 squared is 576, and negative 3 squared is just 9. We add them together. We have square root of 629. And since 629 is divisible by 9, we can extract and simplify this radical. We get 3 square root of 69. So the area of the parallelogram is 3 square root of 69 square units, which is pretty nice. Next, we are tasked to find the volume of the parallelepiped with height z right here. So note that the volume is just equal to the scalar triple product, and we already know the cross product of x and y. It is given by negative 6, 24, and negative 3. So with that product, the vector z, which is 1, 1, 3, and that cross product, negative 6, 24, negative 3. So we have 1 times negative 6 is equal to negative 6. 1 times 24 is just 24. 3 times negative 3 is just negative 9. So we add them together. Negative 6 plus 24 is 18. 18 minus 9 is just 9. And then we absolute value it together. We get 9. So we get the volume of the parallelepiped, which is equal to 9 cubic units. So sadly, that would be the end of the problems. So if you have time, you can review more about the dot product and cross product. So thank you for watching and good luck.